on electricity, you are going to be quiet while we do this so that you're not in the background of the video. Are we clear?
Yes, ma'am.
Okay. Carolee, go get your stuff and I'll meet you over at the table.
What new discoveries are being out there? What new adventures can we see? What are the answers to the never-ending questions in your brain that's in a race to find the reason or the place to be vibrant to outer space? So that the truth of any case can be unfolded in the real world. Science in the real world.
Okay.
Hi, I'm Kirsten. Welcome to Real World Science. Electricity is an important part of our life. Electricity provides the energy to run lights, telephones, computers, and motors. We use electricity every day, but did you ever wonder, what is electricity? And where does it come from? Let's find out. Intro to electricity. To begin with, electricity is a kind of energy that has been around since the beginning of the universe. Even before there was life on our planet, electricity existed in nature in the form of lightning. Electricity even exists inside our bodies. If you could look inside our bodies, you would see tiny electrical signals that zip around, triggering our hearts to beat and our muscles to move. These signals send echoes through the body tissues to the skin. Those electrical signals from the heart can be detected by sensors and displayed as a wavy line called an electrocardiogram. Little electrical pulses in our brain even give us our ability to think. All life depends on electricity. Throughout history, many people experimented with what is called static electricity. You get static electricity when you rub certain materials together to generate an electrical charge. Static means not moving. Static electricity stays where it is made, or at the most, makes a single jump. A good example of static electricity is when you rub your feet on a carpet and then touch a doorknob. The shock you get is static electricity making a single jump from your fingertip. There's another kind of electricity too, which behaves quite differently. It's called current electricity. Current electricity moves. It's the kind of electricity we use every day that travels along wires to light bulbs, computers, and other electrical appliances. In this program, we're going to explore both static and current electricity. Let's begin with static electricity. Static electricity. When you rub certain objects or materials together, you can sometimes cause them to be charged with electricity. Rubbing objects together is also known as friction. For example, friction occurs when you rub your feet on a carpet. If you're wearing just your socks, you could get an electric shock when you touch a metal doorknob. That's static electricity. Why does that happen? Here's a simple explanation. You probably already know that all materials are made up of atoms. Atoms are made up of protons and electrons. Protons have a positive charge and are represented by the plus sign. Electrons have a negative charge and are represented by the minus sign. Most materials are neutral, which means they have the same number of protons and electrons. Friction between two objects may cause electrons to move from one material to the other. When the electrons are added to a material, the material has a negative charge. When electrons are taken away from a material, the material has a positive charge. An electrical charge is a force caused by friction. What happens when an object is charged with electricity? Well, materials with the same electric charges repel each other. Here's a demonstration. As this balloon is rubbed with a piece of wool, the electrons leave the wool and transfer to the balloon where the electrons will stay. That's why we call it static electricity. They stay put, so the balloon is negatively charged. Now, if we rub wool on another balloon, that balloon too will be negatively charged. If we try to put the two balloons together, they move away or repel. Materials with the same electric charges repel each other. Like charges repel. On the other hand, opposite charges, positive and negative, attract. Here's an example. By rubbing the balloon with wool, the balloon has a negative charge. Next, we're going to positively charge a piece of nylon. To do this, we'll rub the nylon with a plastic bag. Plastic doesn't give up electrons easily. However, it will take on electrons and leave the nylon positively charged. When the positive nylon strip is placed near the negatively charged balloon, they attract each other. Sometimes charges between two objects can become very, very strong, and an electrical spark can jump from the negative charge to the positive charge. This phenomenon happens in nature all the time. We call it lightning. Lightning occurs between two differently charged sections of a cloud, or between a cloud and the earth. Current electricity. So far we learned that static electricity doesn't move. Once the electron transfers, it stays put. That's why static electricity is not very useful. However, an electrical charge that can be made to move in a continuous stream or current is used all the time. When electrons move, we call it current electricity. Current electricity is the electricity we use every day to produce different forms of energy, such as light, heat, or sound. In order to get an electric current flow, electricity needs a complete path or circuit for the electrons to travel. Electric circuits are made up of several components. One of the components needed to make a circuit is a source of electric energy, like a generator, a power plant, batteries, solar panels, or turbines. Another part of a circuit is called a load, which is an output device, such as light, bell, or motor. Every circuit also needs a conductor. Most metals, such as copper or aluminum, make good conductors. In this demonstration, we are going to use copper wire. Using this battery as a power source, the bell as a load, and this wire as a conductor, we are going to set up a simple circuit to show you how current electricity works. First, if you look on the battery, you'll see there are two terminals. One is charged positively, designated with a plus sign. The other terminal is charged negatively, represented by a minus sign. You can start an electric current by attaching a wire to one of the terminals, then to the load. The circuit will be complete when the negative and positive terminals of the battery are connected, and the bell should ring. As long as the electric current is complete and the battery has energy, the bell will continue to ring. When the circuit is broken, the bell will stop ringing immediately. Now there is one other component that is a part of most electric circuits. It's a control device, such as a switch that controls the flow of energy to the load. Watch what happens when the switch is attached to our electric circuit. See here? The switch is open, and the circuit is broken, so the energy cannot flow. But when the switch is closed, the circuit is complete and the bell rings. All electric circuits must form a complete loop. However, there are two ways in which a circuit can be connected. The first is called a series circuit. To make a series circuit, all the components must be connected in a single loop, just like the circuit we've set up. In a series circuit, the current can only flow from one path from one side of the source through the load back to the other side of the source. With a series circuit, you can operate a few loads, like 2 lights on the same circuit. The only problem is that if one light bulb blows out or is disconnected, the other one won't work. Watch what happens when one light bulb is removed and the other light goes out. That's because the circuit is broken. But you can set up an electric circuit so that you can operate a bunch of different loads all at the same time and turn one off without affecting the other. It's called a parallel circuit. Let me show you what a simple parallel circuit looks like. A parallel circuit has a source, conductors, and in this demonstration, 2 loads, 2 lights. But notice that the lights are on 2 different branches of the circuit. In a parallel circuit, you can turn off one light bulb and the other bulb will remain lit. A parallel circuit is the type of circuit you would find in your house. Think about it. You can operate a blender, a toaster, and a radio all at the same time. But if you turn one off, the others will continue to work just fine. That's because they operate on a parallel circuit. Entire towns and cities are part of a circuit. The energy source is the power plant. Power stations have generators that push out electricity. Electricity travels along conductors called power lines into all kinds of electrical equipment in homes, businesses, and factories. Volts and amps. Now all this electrical equipment needs a certain amount of electrical energy at a certain rate. Therefore, it is important for people to be able to measure and control an electric current. All circuits, regardless of their size, need energy and a force to drive the current. The force is called an electromotive force, and it gets the electrons moving. The amount of force the battery pushes out is measured in units called volts. The more energy a power source can give, the bigger the voltage. You'll notice that the batteries are labeled with the amount of voltage they produce. Here's a 6-volt battery and a 1.5-volt battery. Generators at power stations can push out 25,000 volts or more. That's much too powerful to use in a home. So along the way, the voltage is stepped down at a step-down substation transformer. The electricity that is used in homes is typically 110 volts. Now, as electricity flows along a wire, scientists are able to measure how quickly it is traveling through the circuit in units called amperes. The amperage, or rate at which the electricity current flows, depends on 2 things. The first thing that determines the flow of electricity is the voltage of the power source, and the second is how well the circuit conducts electricity. Remember, a conductor is any material through which electricity can flow easily. Some materials do not conduct electricity well, and they're called insulators.